Whilst in flight and for the duration of any stay on the lunar surface, the Apollo astronauts would have been totally at the mercy of unpredictable solar particle events. Solar flares could have affected any moon-bound astronaut at any time. A dose of 170 rem could result in vision impairment with a 20 to 30% probability of death within 60 days. Even a relatively low dose, around 70 rem, could result in vomiting, nausea and diarrhea during the trip. Throwing up into a spacesuit is not something NASA would wish to be broadcast live on TV. There was even the possibility of an astronaut dying on the lunar surface in front of millions of viewers back on Earth. Therefore, sending astronauts to the moon with these risks could be described as playing American solar flare roulette.
With the Naval Research Laboratory, NASA launched the SOLRAD satellite. It too studies the sun's radiation and records the disturbances which can disrupt long-range communications and navigation systems. This computer-type picture shows the sun's disk and inner corona. It was returned by OSO-7, the latest in the orbiting solar observatory series. OSO is trying to determine the direct effects solar flares have on the environment, weather, and communications. Earth is surrounded by the magnetosphere, an enormous teardrop-shaped region formed by the solar wind, a supersonic stream of particles blowing on the Earth's magnetic field. It is in this region that a craft like the small scientific satellite does its job.
Einstein once presumed to speak for God when he joked, "God does not play dice." But some would say playing dice with nature is the game NASA played if the agency did indeed send insufficiently protected astronauts through the Van Allen radiation belts and onwards to the moon. So now let's look at this question of radiation and see if and how it posed a serious threat to the successful outcome of Apollo. What in general terms are the dangers of radiation out in deep space? We're not referring to the heat coming from the sun, but the effect of solar particle events, SPEs, including X-rays and gamma rays, on our spacecraft and an unprotected astronaut traveling beyond the protected environment of his home planet. What actually happens when an astronaut leaves the Earth for the moon? A human being leaving Earth for deep space has to travel through the very thick ringed donut of trapped radiation which permanently encircles our planet. This donut contains within it two specific natural zones of very intense radiation. The whole region is named after Dr. James Van Allen, the scientist who registered this discovery in 1958. The innermost zone of the two Van Allen belts surrounds us only some 272 miles out from the Earth's surface.
Entering the Van Allen radiation belt from below, you would see the radiation levels rising considerably. In fact, they're higher within the belt than they are above it, and much higher than they are below it. And then as you got above the Van Allen radiation belt, the radiation would still be very, very high, but lower than this radiation that's trapped within the belt. So those form a formidable barrier to the passage of manned spacecraft within these belts. This radiation varies year by year. The sun has an 11-year sunspot cycle, and every 11 years it appears to repeat. And so every 11 years there's a peak of sunspot activity, and this is associated with a peak of solar radiation. These peaks have been charted from the 1800s all the way to the present. And one of the recent peaks was in 1958, which is one of the reasons they decided to have the International Geophysical Year, and one of the reasons that Explorer 1 discovered the Van Allen radiation belts and all of this type of phenomena. And since then, the next peak was in 1969 and 1970, right when the Apollo missions were supposed to have flown through them. They couldn't have picked a worse time to try to fly a manned flight through this radiation field.
Dr. James Van Allen had pointed out the necessity to shield the astronaut spacecraft adequately, given that these belts of trapped radiation were dangerous to bioorganisms. Since 1962, the Van Allen belts also possess another zone of even more intense radiation, which was artificially introduced by the American military. We suspect that with Operation Starfish Prime, the exploding of a megaton nuclear bomb 248 miles above Earth, NASA was trying to force a corridor through this natural danger zone, but ended up making matters worse. Astronomer Sir Bernard Lovell stated at the time that the effects of this explosion were cataclysmic, both here on Earth and out in space. The radiation created by this engineered explosion was trapped into a third belt, over 100 times more intense than the two natural belts. By 2002, this artificial zone will still be 25 times worse than the most intense zone of radiation trapped within the natural belts. Had NASA not only failed with Starfish Prime to create a corridor, but also increased the radiation risk to unprotected astronauts?
During their research, Bennett and Percy have found that the depth of these Van Allen belts varies considerably according to the source of reference. Despite the fact that numerous probes and the Apollo missions have allegedly traversed these zones of intense radiation, there's little or no agreement on the depth of these zones. James Van Allen stated that they're at least 64,000 miles deep, whereas NASA claims they're only about 24,000 miles deep. Less depth equals less travel time through this danger zone, and as NASA maintains that the Earth-Moon round trip would involve just about 2 hours in the belts, the agency could, and did, just about avoid the issue of spacecraft shielding by asserting that this was too short a time to be of any real danger to its astronauts.
Such a claim is rather like believing that rain will wet you less if you run through it. In reality, whether you move slowly or quickly through rain, you'll tend to get equally as wet. And so it is with radiation, except that with radiation you cannot dry off and return to the state you were before you were irradiated. Radiation is present throughout deep space and alters everything that it comes into contact with. It becomes a part of any bioorganism. Our research findings suggest that firstly, on a return journey to the Moon or Mars, an astronaut would spend around 4 hours within the trapped radiation of the Van Allen belts. And secondly, that to protect human beings adequately for the duration of such a journey in the late 1960s would require a spacecraft far too heavy for any of Wernher von Braun's rockets to launch.
But we're getting rather ahead of ourselves. We'll come back to von Braun's Saturn V rocket shortly. In an interview with researcher Jim Collier in the late 1990s, Dr. James Van Allen said that he stood by his evaluation of the depth and danger of the belts.
There are cosmic rays in space. You have the radiation flux that you have to deal with out there. We understood that. We monitored the sun very, very carefully. We did not send expeditions to the Moon at times when there was the possibility of a particle event on the sun. We didn't want to subject the astronauts to any radiation that could come flying off the sun from a solar flare or a prominence or an event like that. But we thought it through very carefully, and we planned our way through that.
NASA would have us believe that to send its astronauts through space at the height of solar activity was a matter entirely under its control. But it's impossible even today to predict when debilitating solar flares are going to occur. Predicting earthquakes is virtually impossible too. This is the aftermath of the Turkish 1999 quake that came with no warning. And again, the Taiwanese 1999 earthquake.
So if the prediction of solar particle events is impossible, what were the means of protecting a crew when travelling through deep space in an unshielded, thin-walled rocket ship?
You could use propellant, structure, other parts of the craft, the heat shield. You would design it so that you would maximize the amount of material between you and the sun for the flight, but try to avoid carrying any material just for the sake of the shielding. It would serve a dual purpose.
With aluminium shielding, it's accepted that the minimum requirement is a thickness of 10 centimetres all around the craft. Was there any attempt to provide such protection?
No. The walls of the craft were made as thin and light as possible. The Apollo capsule itself was made unusually thin. In fact, they couldn't even initially carry enough air inside to be the equivalent to sea level air pressure. They ran it at reduced pressure in order to be able to make the walls thinner. And then the LEM and other parts of the craft were all made out of very thin material, very flimsy. Almost no protection at all against solar radiation.
So why not try using a solid shield to protect the astronauts from these dangers?
Well, they didn't know how to put a shield like you suggest and still be able to make the weight capability of the Saturn V and carry everything to the moon. I believe that Wernher von Braun's team was basically assigned the task of designing a rocket that theoretically could take men to the moon if everything worked and if there were no substantial solar radiation. But the kind of rocket that they would have had to have in order to take people to the moon, taking into account solar radiation, would have been a much more massive vehicle, and they just decided that this was not something that they needed to deal with. They would just tell everybody that the radiation was okay.
A spherical structure enables a craft to withstand a greater amount of internal pressure. The Soviets knew this simple fact, and the designs for their spacecraft were always spherical. Here's a typical Vostok capsule. Compare this with the American thin-walled CSM design.
If NASA didn't know how to protect astronauts from radiation in deep space, it had not been for the want of trying. During the Manhattan Project and for years afterwards, the American government subjected nearly 250,000 Americans, both military and unwitting civilians, to the effects of radiation. These enforced tests provided data on how solar radiation might affect future astronauts. During the experimental detonations of atomic bombs, American military personnel were ordered to walk towards ground zero, totally unprotected. They were ordered to walk straight into the radiation zone, so that their masters could acquire an extensive information base relating to the injuries and damage caused to human tissue by those in close proximity to this radiation.
The surface of the moon is, of course, above the Van Allen radiation belts, and it's exposed to direct solar radiation. In 1959, they sent a spacecraft that flew past the moon. So that spacecraft could easily have, that one or others that followed it, could easily have contained instruments that showed them how lethal the radiation was. You don't need live animals to prove that something can't live out there. You can just send instruments that will show you that the radiation is beyond what can be withstood by animals or humans.
Solar flares and other storm systems on the sun can create enormous, tremendous surges of radiation. Now that radiation is not only potentially dangerous, it could be lethal to those who are outside our atmosphere, which basically protects us. All right, it can cause problems with radio storms and the aurora and things like that. But with major storms, there is a dramatic threat to those who are outside the Earth's atmosphere. And this would have happened with the Apollo missions. Of course, if there had been a major solar flare during an Apollo mission to the moon, it would have been extremely serious, to say the least.
The versatile IMP, 8th in a series, is exploring interplanetary space and the outer fringes of the Earth's magnetosphere. It also provides warnings of possible solar flare radiation hazards to moon-bound astronauts.
No major incident occurred, but it could have been potentially very, very bad, lethal, in fact.
Remember, solar flares occur all the time. It's the degree of their severity that varies. One of the most severe solar flares ever recorded occurred in August 1972 between Apollo missions 16 and 17. This single flare would have delivered 960 rem of virtually instant death to any inadequately protected astronaut out beyond the Earth's atmosphere and magnetic field. Surely reason enough for the space agency to play safe and adopt the surrogate option as prediction of these events is a very inexact science indeed. Yet the named astronauts were wandering around on the supposed lunar surface in nothing more than what amounts to a thick linen suit. These pressure suits might have allowed for some micro-meteorite protection and possibly maintained an appropriate temperature for the astronaut, but they certainly did not qualify as adequate protection against any unexpected burst of debilitating radiation from an SPE. And as if that were not enough, despite strict medical instructions, in some cases these astronauts neglected to use the protective gold visors to shield their faces. Whether this was whistleblowing or sheer arrogance, it is certainly another example of inconsistency in the record, over and beyond that of image manipulation. Forgetting the astronauts for a moment, what indeed could this solar radiation do to the images? We know, for example, how X-rays can affect film on Earth, and we know how the photographs of the damaged Chernobyl nuclear power station were badly fogged from radiation.
You have an enormous amount of radiation in space, and potentially it affects film, of course, and of course, as you will well know, its prime effect is on contrast.
We took a latent image recorded on the film of a color test chart and exposed it to 8 MeV X-rays. The lowest radiation dose we applied to the film was 25 rem. The latent image, if it hadn't been subjected to radiation, would look like this: a good quality, high contrast, color transparency. After exposure to the 25 rem radiation, the image is almost entirely obliterated. This means, in my estimation, a dose as little as 5 rem would seriously undermine the transparency. It would look significantly fogged. It would be a very thin image.
If you look at the results, top quality duplicates, you can see that there appears to be no effect whatsoever. It never got to the stage where I heard, at least, that a film had been badly affected by temperature or the pressure differentiation or radiation.
I would expect to see on the transparencies evidence of small bright dots where a high-velocity nuclear particle had impinged on that film. I have no evidence whatsoever that this has occurred. The good place to look for it is on the regions of the film which haven't been exposed in the camera, the black spaces, as it were, between the frames. We're protected on Earth by a nice thick atmosphere, and that combined with the magnetic field keep these ionizing particles away from us, on film of course. In space you're not offered that protection. To prevent an ionizing particle, one of very energetic particles that you get in space, from damaging the film, you would need a significant thickness of lead protecting that film.
So if the film exhibited no signs of radiation damage, then surely the camera itself must have been protected. Was the Hasselblad lunar surface camera shielded from radiation?
Well, the original ones were not protected at all. The ones they brought to the lunar surface were painted silver.
The temperature, of course, is very, very extreme on the lunar surface. In the sunlight you could be easily as high as about 200 degrees Fahrenheit, and of course in shadow areas and prolonged shadow you could be in minus quantities.
As far as I know, they had no trouble with overheating of the film, and I think it worked for them, because I didn't hear any complaints about the film getting too warm. On the other hand, they might have had some trouble if the film got too cold, because then it cracked.
Would any of the problems cited have anything at all to do with Kodak's strange reticence to capitalize commercially on the film used for the lunar surface photography?
Although various films were tried by NASA, to all intents and purposes it was only Kodak film which was used during Project Apollo. And I think, and one understands it, I think that the corporate management in Rochester was concerned about a monopoly situation. I think that was the reason, you know, and it's sad in some ways because there was an enormous amount could be made of the fact that it was Kodak film being used.
Okay, let's see, how do I do this? F11? At 74, click.
Okay.
Click. 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 Okay, Tony, do you want me to change the mags on the
EVA
16? It's about empty. Click. That's affirmative. Per second runs it through there.
Right, go ahead.
Okay, will do.
Should be MAG-R.
Click. Okay. Man, if I get this top of this and that picture, it's going to be a miracle. Click. Okay, Tony, during this pan, I've moved about 2 feet downslope, so I don't know what things are going to match up too well or not.
We'll make it work.
And if both the film and camera had problems with heat and cold, then how did the astronauts themselves stay cool? It was the job of the life support system, the PLIS, to regulate the body temperatures. How did that backpack actually keep an astronaut cool and likewise warm when they were working in the cold of the shadow areas?
Somehow they would have to radiate the heat away, and that's not an easy task because the rate that heat is radiated away goes up according to the 4th power of the temperature difference between the radiator and the surrounding medium. So you have to have a pretty hot radiator to radiate away a substantial amount of heat. It would be more likely that you would eject steam, because in taking the heat away from the astronaut, that heat would be used to heat water up and produce steam. So you should see venting of steam if they're using water for this purpose, rather than ice, actually.
We never once saw any ice crystals or indeed steam emanating from the vicinity of any astronaut, either spasmodically or on a regular basis. Not one piece of TV coverage demonstrates such an effect. Interestingly, many researchers, including Ralph Rene, also seriously doubt whether the PLIS had enough capacity for the job in the first place. In this part of the program, we've looked at the dangers of radiation and the serious problems to have been overcome on any journey to and from the moon. Clearly, in the 1960s, no one had the ability to deliver a guarantee against astronauts dying in space. This reason alone would have been sufficient motive for the falsification of what really happened during Apollo.